So now that we've been looking at shear stresses and shear strains, we have to look at the deformations associated with torsion. And for the deformations associated with torsion, really what we're talking about is the angle of twist. Okay, we've already got a little bit of information on the angle of twist. Remember, it is that helix. As the helix is twisting along the member, it is a function of the distance x from the support, but it's increasing constantly over the section of constant torque. So we have our differential element back on the screen, and we remember our relationships between our shear stress, our shear strain and d theta. So let's put out what we do know. So again, related through the length bb prime, we know that d theta is equal to gamma dx over rho, and that was derived on a previous slide. Remember, that is just equating gamma times dx is equal to bb prime, as is d theta multiplied by rho. We also know Hooke's law, so shear strain is equal to shear stress divided by the shear modulus. And we have the torsion formula that we previously derived. Now in this case I've just expressed torque and polar moment of inertia as functions of x. And that's tau is equal to t rho over j. So we're going to combine 2 and 3 together. So we're substituting in 3 for the torque in 2, and we end up with t rho over jg. So it's bringing the shear modulus in, and then we can substitute 1 into 1 and integrate it. So all in one step. Then instead of d phi, we have phi because we're doing the integral over the length, and we end up with our torsion. The rho's cancel out, so we have our torsion dx divided by our polar moment of inertia and the shear modulus. And that would simplify then for members of constant cross-section subjected to constant torque to be the angle of twist between 2 points from one end to the other would be equal to the internal torque over the length of which it's applied divided by our polar moment of inertia and our shear modulus. Now, we should be noting that that is very, very similar to the formula that we used when looking at deformations due to axial load, delta equals PL over EA. And if you're starting to understand and become comfortable with delta equals PL over EA, you should be a step up towards appreciating how we're going to apply phi is equal to TL over JG. So let's get on with applying it. So we've got our example. So this is the same example that we've been running up until now. And I'm going to give you some lengths for the section because we're going to do angles of twist. Up until now, we haven't had to know the distances between A, B, C, and D. So I've added the lengths shown here. We already have done the free body diagram and derived the reaction at A. And so we don't have to do that again. That's already done. And as you will recall, you went on to do the torque force diagram. So that is our starting point for this. Now what we want to do is to look at the angle of twist, again for the solid and the hollow shaft, and we want to be able to plot the variation of angle of twist over the entire length of the shaft. And so I invite you to follow the link that's on the screen and go off and see that problem solved out longhand. There's a second example, and this is one to get practice because, as we've discussed, this course and the skills associated with being effective in this course have a big demand of being practiced in doing it. So here's a second example. Now the other thing I'll point out is it looks like a power transmission problem, but it is and it isn't, because the torques are actually given for each of the gears in the image. And so you don't have to do that power transmission step that we saw in the previous one. It's a straight up torsion problem. So again, I invite you to follow the link to this example. It's done out longhand and absolutely worth the value to go through these, line by line, so that you can grow a skill and appreciation of how to do these problems.